Good afternoon. Before I begin my talk, I would really like to thank the organizers for giving me this opportunity to present. It's a fantastic conference and the lineup is amazing, so I'm really grateful to be here. I would like to thank the volunteers who are helping us, and finally all of you. We have so many fantastic tracks going on parallelly, so I'm really glad to see you folks over here. Now, about the talk. Today we shall be talking about scaling and re-architecting Confluence Cloud architecture. Imagine it's just a normal day for a work. You would expect, to get all your regular tasks done, and all of a sudden you start getting paged. There are a lot of issues with the customers having problems accessing the Confluence instances. You would think that, it's only starting with a single region, and the next region comes out. You would start with US East, then you start seeing failures with West. This is a true story which has happened last year. We had a series of incidents, massive incidents, which just took down our instances, and our tenants and our customers faced a lot of issues. So this talk is going to cover all of these incidents, how we went about addressing these issues at scale, and then how we are re-architecting things for stability and resiliency in the future. My name is Bhakti Mehta, and I would love to walk you through this journey of Confluence. Before we get started, a little bit about me. I am currently a principal engineer at Atlassian. In the past, I've also worked in a startup called Blue Jeans Network. It does video conferencing in the cloud. Before that, I was at Sun Microsystems, and then which was acquired by Oracle for around 13 years. I am a contributor to numerous open source projects, and Glassfish Application Server being one of them. I'm also an author of 2 books. I think I have short-term memory loss because I forgot how hard it is writing the first book, and I still went ahead and wrote the second one. So this is one of my first books, and this is the other one. So about Atlassian, if you could please raise your hands if you've used at least one of these Atlassian products. Fantastic. I'm in the right room with the right crowd. So yes, Jira is the darling. I'm sure everybody must have used Jira. Confluence is the next mothership product from Atlassian. These are old products which have multiple offerings. There is the on-prem, the server offering, and then there is the cloud offering also. This talk is mostly covering the cloud offering for Confluence. Apart from Jira and Confluence, which are the most known ones, you could see there are a lot of other products and offerings which Atlassian offers. So now let's talk about Confluence. Confluence is multiple things. It's a knowledge base, it's a wiki, it's a place where teams document, where teams collaborate. So it's a single place where you would have all your documents. Within Atlassian also, we use Confluence heavily. We have a lot of remote teams, and this is our go-to place for any of our collaboration. We have decisions, we have actions, we have documents, we have DASIs. All of that is written in Confluence. So we dog food our own environment extensively. Okay, how did Confluence start? So the first offering was the on-prem offering, where there would be a WAR and files which would be given to the customers, and then it is deployed on the customer's site, and there would be IT admins who would be running the product, so they're managing it. So that is the server offering. The next offering was to move to cloud. So in 2011, the way we started off was we started provisioning VMs for every tenant. A tenant could be any enterprise who would be interested in having a Jira or a Confluence instance. So what we would do is provision a VM in our data centers, and that would be running the code for that particular tenant. As you could think, this would have its own set of issues. Firstly, these VMs were not easy to scale. So there were size restrictions on, which enterprises could be moved to the cloud. So, if it's a larger enterprise, you would not be moved to the cloud, you would be still using the on-prem. Over the time, cloud offerings have matured. VMs are not the way to go. There are a lot more mature cloud providers which we could utilize, AWS being one of them. And we also noticed that there was, as new tenants want to get onboarded, there is a lot of cost and effort to onboard a new tenant. You have to procure the hardware, you have to get it set up. Releases take longer because every VM has to be updated. So even though this was the first offering for going to the cloud, this was, it had its own set of limitations. So enter the journey, and we went on to the next offering. The next one is a multi-tenant architecture. I would just go over this gradually with you. So it's multi-tenant, it is highly available, and it is microservices-based architecture. We use AWS heavily in our infrastructure. Our tenants could be in any regions. We have deployments in 6 regions of AWS. So we have US East, US West, then we have 2 regions in EU, and 2 regions in Asia Pacific. So what we would do is, wherever our tenant is, our customer is, we would find the region which is closest to that tenant, and then deploy in that region. So this is just an architecture of one region deployment of 30,000 feet high-level architecture. It's not as simple as this looks, okay? It's just top-level blocks, but it's way, way more complicated inside. So let's just go over this. So we would have a customer. The request would go through the Global Edge proxy, and then we have some internal routing, which would figure out from the request path which tenant it is and route it to the right region for the tenant. Within a region, we have our own shards. A shard is nothing but just a logical grouping of a bunch of tenants and giving all the infrastructure for those. So there are these services at the routing layer which would be contacted. One is the user level service for the figuring out the details for the user. The other is the tenant level services. So it gets you all the details about the tenant. Once the details about a tenant are known as to which region, the routing service actually routes it. There would be an authentication and authorization happening. And then typically you would have the Confluence code which would hit, which would have its own databases and its cache. So it looks pretty simple. There is some routing layer which finds the details, routes the request, and then you would think about the databases and the caches. So how does this architecture have advantages compared to the previous one, which was just the VMs? Now we have quicker deploys, faster deploys, because previously every VM needed to be updated. It used to take us weeks to go and update. Now we actually deploy this twice a day, so we are that fast in deployments. For tenant provisioning, there is not much we have to worry about because we have 6 region deployments, we have all these EC2 instances, and if needed, we could add them elastically. So if a new tenant is onboarded, we have the infrastructure. You just have to figure out which is the closest region the tenant should be routed to, and then provision the tenant over there. We get the scale. I mean, we are looking at billions of requests per day. So with AWS, we get the compute. We have a lot of our own tweaks to do to get the performance at scale. We do get the resiliency. So the way in AWS you would have multiple availability zones within a region. And we internally do a lot of these tests ourselves. We would bring down an AZ and see requests should just automatically fail over to another availability zone. So we get the resiliency. We do get elasticity. When peak traffic comes, we do scale out. So with AWS, you can get the elasticity. So this gives us more potential to onboard larger enterprises. Previously, we were just using VMs where we couldn't get the larger enterprises. Now with this infrastructure, we could definitely move on. We do have microservices which are deployed in all these regions. So, we can reduce the blast radius by sharding these microservices across regions. So, if some problem is noticed in, say, US East, if we make a quick fix, we would hope by the time the other regions come up, we could still not affect all the tenants. So there is some sort of, blast radius protection with these multi-region deployments also. The process which we follow currently is everything is released off master. Any feature is gated by a configuration and dark launched. So the way that works is, say, UI or on the backend, we are building new features. You would never roll it out 100% to all the tenants. We start off with, say a 5% rollout. You watch your metrics, you watch how the customers feedback, or if it's like a new UI feature, you are looking for that feedback. Then you could roll out to say 10%, 25%, and then finally you would go to 100%. So we do a lot of these conservative rollouts. So anything is always wrapped in a feature flag, any change, and then you would just roll out based on, as you keep watching the progress. We iterate fast because we deploy twice a day. Teams can work fast, but we are also conservative in terms of rolling out. So, that we leave it to the discretion of the individual teams. You can merge your changes, but, you could figure out when you want to start rolling out the features. You might be rolling them back also if you don't get a positive response. So all of that is the onus on every team. So we can iterate fast. We collaborate very easily. So, there might be two teams who are dependent on a certain feature. You could still push it out, and then you all could decide on which tenants you all want to start. Try this on low traffic tenants, try this on X% of requests. So all of this collaboration can happen very easily because we are going this fast, but we are also going conservatively. And we've also, over time, built a fast revert policy. See, when you are going this fast, outages may happen, bad code changes can get in, config changes can get in. So the way you can, reduce your pressure during these stressful times is if you have a good revert policy. So what you would like to do is, say if an outage happens, the first thing you do is revert back your code. And then you can analyze which was the bad commits or, a set of commits or configurations which caused these outages. So we do have these checks and balances in place. About our deployment platform. So this is the application level. We also have a team which provides us the basic deployment infrastructure. It is similar, like, you could think of like Kubernetes. We are moving towards Kubernetes. Currently, we have our own platform, which we have a set of tools. So it takes our YAML files, converts them into AWS CloudFormation templates, and provisions resources for us. So it is the orchestration framework, and we have an underlying platform team which helps us. That takes care of logging, monitoring. So some of those functionalities are provided to us by the platform team, and that helps us to deploy safely. So when we do a deploy, we will have health checks just to see, if the node has got all its dependencies set up, and then the node would respond back that, yes, I'm healthy. So we would take care of automated health checks. We do canaries which get deployed. So you would deploy it as, again, just like our features, you would do progressive rollouts, a 5% rollout of the traffic, then a 25% rollout, then a 50%, and then 100%. So we deploy over an hour, and you are watching for monitors to see if there are too many error rates, then it's a bad deploy, it automatically gets reverted. So these are the checks and balances we put on the deployment side. This is the normal flow of how any developer's commits reaches production. The first thing would be a commit would be merged. We would then have automated tests. It goes to a staging or a dog fooding environment for a while. And after that, there is some post-deployment verification checks which happen. And then finally, that gets deployed to production. So in the best case, if a developer has merged a commit today, the best case, it might just go to production the next day. So, with all these tests and checks and balances, and we have like twice a day scheduled deploys, so it might hit production on the next day. So, with all of this sounding fantastic, what actually happened during those incidents and what was actually going wrong? The way it was that we had a database, so we have provision within an SQL box, we have databases for every tenants, and that way it ensures that data between one tenant is not leaked to another tenant. But then we have other resource constraints also in a multi-tenant architecture. The biggest one is database connections. So what was happening is at that point was, database connections are a bottleneck in a multi-tenant architecture in the way we had designed it at that point, and we ran out of database connections. So even though those MySQL boxes were gigantic, and it should a normal thing you would expect that database connections should only last over for a few milliseconds. There was a bad code, and those connections just took longer. And that was because we were trying to log and get some metrics, and there was some synchronized block which started holding connections longer, and the connections were not sent back to the pool, and finally we started running out of connections. And what happens is when a database starts running out of connections, then all the HTTP during peak traffic, HTTP requests are also hitting, and they are retries, and then everybody's trying to acquire connections, and you're already in a bad state. And at some point, you'll just start seeing 500s. So it was not a very good state for us to be in. Over time, yes, we did architect, we figured out what was wrong. Of course, the first thing we did was revert the commits. So things did stabilize. It wasn't as bad. And then we also, during that time, there are asynchronous other workers also who are trying to do their jobs, and they are also trying to pull from the database. So we started back pressuring them, so throttling those asynchronous jobs because those could wait, let the HTTP traffic get the connections. So there was a lot of things we did during that incident. And then post the incident, there were postmortems, and we analyzed it. We went through and fixed a lot of cases where, database connections were getting abused, and we got the system to stability. After that, there was another move was like, yes, this works for now, but we need to rethink and re-architect for the next scale in future. So the next few slides will tell us about our journey on how we are planning and re-architecting this next phase. So why do we need to re-architect? Even though, you've seen the journey from VMs to moving to AWS, highly available multi-tenant architecture, to the next phase. These are the needs which cause us to do the re-architecture. One is bottlenecks when you're trying to scale. Databases or any of these resources, there are always going to be bottlenecks. We are trying to reduce these bottlenecks at scale. We need to take care of fairness in a multi-tenant architecture. When you have so many tenants sharing resources, you have to ensure that you are fair to all of them. You cannot have one tenant taking up all the connections and all the other tenants paying the price and suffering it. So we do have some of these checks in place where we ensure that everybody is given certain limits, like, say database connections, if tenants. So you would not have one rogue tenant taking down a system. But we want to still ensure this in future. We have to improve developer velocity. Right now, some of this code, even though we have smaller microservices, a lot of this code lies in a monolithic code base. And what happens is, as our teams are growing, we want to improve developer velocity, but then we can get stuck because of, so many changes going in together, tests failing. So you have to freeze the pipeline, figure out why the tests are failing. So it slows things down when there are issues. So we want to improve the developer velocity. That is another reason we have to re-architect and rethink some of this. We have to reduce the blast radius for impact. Since a lot of this code is in the monolith, if something breaks, most functionality gets affected. This is not the way future services are architected, right? Even though if, say, you have a billing system, you might have a notification system. If the billing system is down, the notification system could still work if things were isolated in their own functional units. So we need to also reduce the blast radius because of that. We need to provide more features for our customer and quickly. So that is another reason, when people are working in the monolith and, if the pipelines are frozen because of changes, we cannot move as fast as we would like to. So the re-architecture helps us to move faster. So the best way to re-architect from a monolith is the world of microservices. So further going deeper into microservices. So everybody knows microservices and all the benefits the microservices provide. So first is simplicity in the architecture. So, every component will just do that stuff, what it's supposed to do. You have your own functional encapsulation. You're not dealing with anything else. So, you have your own unit of work. Your isolation of problems. If there is a problem in one service, it does not impact the rest of the services. So the microservices ensure that. Easy scale up and scale down. So, every service could be scaled based upon its usage patterns. The deployments are easy. Every service could have its own deployments. And it also gives you polyglottism and heterogeneity. So with polyglottism, each team could have their own stack, their own preferred language, deployment platforms, as long as they are able to talk the common contracts of whatever is decided and agreed among services. Each team is allowed to evolve in its own way. All this sounds amazing, though in reality, microservices have their own set of challenges, and we can talk about those later. So nothing is that looks too good is always that good. There are its own set of challenges. Now, so as we are building these new services, which we are, the core requirements for us are multi-region deployments. So we need, as I mentioned before, our tenants are in 6 regions. We need to ensure that you have these new services in all the regions so that you are not paying the latency of a cross-region hop. So we have multi-region, all these services should be deployed. They need to be highly available. We are also trying now to test. Previously, we were doing only if an AZ availability zone goes down. Now we are also trying if a region goes down. So say if there are issues in one region, the tenants could be routed to another region and it should still work for them. So now we are trying to architect a step further and trying to design for region failures. They have to be extremely low latency. I shall cover some of the services which we have built, and we are looking at around less than 5 milliseconds P95. And it is extremely hard to achieve that, and we've done some of these services, and this is our goal continuing future. So as you are adding all these components, latency becomes really, really critical. And we have to ensure we do a lot of tweaks to achieve that level of SLAs. And we also have to ensure that it is secure. So we have some checks in place like encryption at rest. We ensure about that in all the databases, encryption in transit. So we ensure about that there is a lot of security also because it's our tenants' data which we are talking about. So as we are re-architecting towards these new services, these are some of the choices and considerations we have made. We using NoSQL heavily for all of these services. And we use everything in AWS, so we use Dynamo for NoSQL. How many of you all have worked with Dynamo over here? Okay, yeah. So we've got pretty good performance with Dynamo. The next layer which we've added is DAX. So DAX is the caching layer in front of Dynamo. And that gives us these under a few milliseconds and all latencies, and it has extreme caching, so that helps us. We use Spring Webflux, which is completely reactive, non-blocking, async. So we use that extensively to get this performance. We use this completely, it's built over Netty. So we use Spring Webflux extensively. We've also started experimenting with Kafka. So every region will have its own Kafka deployments. We've done, so far we've been using SQS, but we did notice that SQS was giving a little more higher latencies and we could achieve and work faster with Kafka. So we've started moving towards Kafka. We use libraries like resiliency4j. This is for circuit breakers and timeouts, and all these configs are over here. So, whenever you are making connections, you will have all of these with resiliency4j. So it will give you your retry policies, your timeouts, and all of that we configure. For our testing, we use WireMock. So we do, of course, the unit testing, and then we do all these integration tests. We use a lot of WireMock. So this is a typical, any new service we build, we have some of this already platform boilerplate code. So it's very easy to start building newer services. And most of these services would use these components. For all the new databases, whether we are using Dynamo or Kafka, we do worry about encryption at rest, and we ensure that we have those policies set up before we provision databases. We also, just like the monolith, we do ensure we have quick deploys, and we follow the same thing. We have scheduled deploys every day. So you would push a change, it goes to staging, and then it goes to production. The biggest factor over here is constant evolution of metrics, alerts, and monitors. As these services are evolving and all of them are starting to take production traffic, we are always watching for dashboards and metrics and monitors, watching for latencies, watching for production issues in any regions, figuring out how we can get things better. So these are the considerations we follow for any of the new services. If you all have questions, feel free to stop, or otherwise I'll leave some time towards the end. Now, does anybody know what this image is? It's a Hoover Dam. For those from US, this is one of the largest dams. It's an architectural wonder. Colorado River is one of the longest flowing rivers, and there was this Hoover Dam was built on top of the river. So why I am talking about a dam in this talk? So one of the biggest prerequisites for building a dam, what was to create diversion tunnels. How can you build a dam when there is flowing water? The first thing they did is build diversion tunnels, which routed the water in another region. So then you start building the dam. This is exactly the same stuff what we are doing when we are starting to build these new services. So again, we are talking about the same architecture, except I've added a new block over here, is all the new services which we've added. So this is our equivalent of those routing tunnels. You have these billions of requests going in, and what we are trying to do is you have this is the old stack, which is exactly what I covered in the previous slides, and we are parallelly building a new stack with all these microservices. What we have built is this whole routing layer in between. So as the request comes, previously it used to always go to the old stack. Now, based on certain criteria, we have these services over here. Partial request starts going to the new stack. Our aim is over time, you would start redirecting more and more requests to the new stack as the new stack starts getting built and becomes more stable. And finally, you start decommissioning a lot of stuff from the old. So this is very much similar to how the dam was built, how we are routing traffic, and how we do this in production. Now, since we've added this whole layer on top, it becomes very critical for us to do it at sub-millisecond latencies and be highly available. If this layer fails, everybody is going to notice it. Our customers are going to notice it. So when we build these services, we have to be extremely aware about the performance and how critical these services are. If anything gets broken with these services, we do get paged and woken up at night, because this is highly critical for every traffic. So with these services, I will be doing a small dive into these services, what we built. But this is the routing layer. So you would have the requests which would go to a proxy. The proxy is built with Nginx and Lua. And then it actually consults another service, which we are calling like a ledger. It keeps an entry for this tenant, for this content, whether to route to old stack or a new stack. And based on those routing rules, then the request is redirected to either the old stack or the new stack. So this is the first set of services which we have built. So what we achieved so far? Yes, high throughput, because we are still looking at billions of requests. Every request still goes through these services. We have achieved the P95 5 millisecond latencies with the Dynamo and DAX and extreme caching. We have got that, and we do have fallbacks. If we don't get the responses in this much time, by default we route it to the old stack. So we do have those fallbacks in place. Multi-region availability, so again 6 regions, all deployments, and then latency-based routing, so that if one region is not responding, the next request by latency-based, you could go to another region and still it should work. Completely non-blocking, reactive with Spring Web Flux. It is very adaptive, so we have put in a lot of auto-scaling rules, and we've made it completely interventionless based on certain parameters so that the nodes just scale out. And we've replicated the state and behavior completely. It's all interventionless, so that in most cases, it just works. Of course, initially there were teething problems, and we used to get paged a lot, but things we have smoothened over time. So this is the new way of life. We build these services, we run these services, we own them completely. It's a completely DevOps model, and then we also plan for future. So we are also thinking ahead of, based on our traffic patterns and how do you architect for future scale. What were some of the challenges which we ran as part of building it, and how we overcame it? So, as when we build these services, there are a lot of operational stuff. Like, given this tenant content, is it old stack, new stack? You don't want to be doing it when you are paged or something. You want operational runbooks. You wanted tools. So we built a lot of these operational support UI around it also. Because, if any of these REST resources, you don't want to be finding out what are the right headers to be added and all of that during a peak pressure time. So we've done a lot of support and operational stuff around it also. So any frequently used operations which you think you might get paged for, and if you need to be looking into it, build UIs for it and make sure that, that is available. There are runbooks for it and people are trained for it. One of the other things which helped us was scheduled auto-scaling. When AWS instances are scaled out, we noticed it takes time. It was taking us around 6 to 7 minutes to scale out. Now, during that time, our P90 latencies and all used to get impacted. So what we started doing is, we know our peak traffic may be around 9 o'clock in the morning. Let's start scaling from 8:15, go a few X number of instances, 8:30 by 9, we've got extra instances ready to take the load. So, you don't waste time auto-scaling. Similarly, scaling down. We know traffic starts going down after hours, after 4. Start scaling down gradually. So, then you save on the cost and the tenants don't see any bad performance. So we started doing a lot of scheduled auto-scaling to get the peak performance. We use Route 53, latency-based routing. So what it does is, when a request comes for the tenant, even if the tenant is based in Sydney, if you as a user are based in Europe, you don't need to be routed to the APAC region. You could be routed to the EU region, and your data is always replicated across regions. And so you would see the best performance for individual users. You don't have to go where you are, because there could be headquarters of companies in certain regions, but there could be remote employees. So you don't have to make those calls to that long region and suffer the network hop. And this all is enabled because we have global replication of the metadata. So using Dynamo and global tables, we replicate a lot across these 6 regions. And that helps us to route a request to any of the regions and get back the response. Metrics and monitoring. This is an area which we focus the most on. As soon as you roll out a new feature, you want to watch for the performance. You want to look at metrics, monitoring, and dashboards. So this is an area which we really emphasize. We use Datadog. We are now moving towards SignalFX, but it doesn't matter. We've used New Relic also. So whatever metrics you all are using, please ensure that you all are watching out for spikes. We watch for CPU performance, memory utilizations, I/O weights. So all of that we are watching out. So where are we now? Before, we still doing this re-architecture. We were seeing initially last year, like there were bottlenecks at scale, and which used to cause outages. Of course, we used to ensure that we try to recover from these outages as quickly as possible. Now we have started moving towards these newer services. We'll have a lot more services, independent owners who are responsible for their services, their elasticity, scaling them out. Of course, there are SLAs. For any new service which is built, there are SLAs, and we want them under a few milliseconds because, you don't want to be worse than the current architecture we have. You have to always aim for lower latency performance. We are trying to start gradually decompose the monolith and start reducing. Initially, it was single database, and that becomes the point of failure. Now we are trying to move the data across these smaller services, so you don't reduce the single point of failure issues that, once the database goes down, everything goes down. Now, if there is an issue in a service, if that service goes down, you might see partial degradation, but you're not going to see a complete failure. So that is what success looks for us. So you have to reduce the load on the monolith. You ensure that there is, a partial degradation, and of course you could have good fallbacks for it so the customer doesn't even notice it. But overall it helps improve the performance. So what are the lessons which we have learned along this journey? Errors are frequent. You have such a big team, people are always committing code, and yes, there could be bad commits, bad configs. That is frequent. That could always happen. But it is those latencies which are the consequential ones. The latencies are the ones which would start killing us. I just gave you one example of an outage where there was a synchronized block which took over the database connections, which started causing these cascading failures. So watching out for latencies is extremely critical. That is why, as we are moving to newer services, we are really focusing on what our P95's latencies are looking at, further ahead. So we want to keep focusing on latencies and architect for that. Limiting access to resources to avoid noisy neighbor issues. So because it's a multi-tenant architecture, you would always want to start limiting your access so that everybody has a fair performance, and at the same time, not one rogue tenant could take down the whole system. So having throttling in place, rate limiting in place, all of this definitely helps build your system being more resilient. After these services, the next services which we've started building is starting to do dual writes. So now the monolith is writing stuff in the database, and we've started building a new service which will asynchronously start populating it via Kafka into the new data stores. And gradually, we will start flipping the primary and the secondary. So right now, the primary is the initial monolith, and the secondary is these new services. As those services become mature, we will start flipping that so that the primary becomes the new services and the secondary is the monolith. And then we start doing the reads from the new service. So that's where, we had these routings in place, and that is our evolution for the future. That we will have these new services in place, and they would start rendering all the data, and you start gradually decommissioning and reducing the load on the monolith. So that is our eventual vision, and I think in the next few months, that is what we are aiming for. So one more thing. The last thing, which is scaling, is just a continuous effort, because as we are growing and as our customer needs are growing and larger enterprises are coming in, this is something which we have to keep revisiting and evolving over and over time. So you cannot say that, oh, what I worked like last year, it may or may not serve there. You have to keep tweaking it, tweaking the knobs. We are always looking at all our thread pools and all of those changes just to see that we can ensure that we can scale further. So it's always a continuous effort. In the past, I have this cheat sheet. I keep joking that, I just ran out of real estate and I couldn't continue till Z. But, these are some of the checks and balances which we have where, from A to Z, where we have these alerts, we have bulkheads, circuit breakers. So if you all are interested, and if you want to ask any about this, please let me know. I just ran out of place, and maybe for the last few letters, I could keep this on. We have around 10 to 12 minutes. So if you have any questions for me about the old architecture, what our vision is for the new architecture, and what are the challenges we ran into, I would gladly take them. So let me know what questions you have for me.
Yeah, you said you have old stack and new stack.
Yes.
Does it mean that if you add a new feature,
Mm-hmm.
you implement it twice?
Fantastic question. So the question was that we have an old stack and we have a new stack. So does that mean if a new feature, would you implement it twice? It depends. Now what we started to do is new features, you would try to start building on the new stack itself, because you don't want to implement it twice on the old stack and the new stack. So we would just try to start putting it on the new stack. Again, it depends on the feature also. If there is something which will need a lot more building, like UI components in the new stack and all, and they might not be ready, then we might have to consciously take a trade-off and still put it in the old stack. So it's a journey over time. So if it is something which could easily be moved in the new stack, that is our first choice. And you would want traffic to get routed to that. There are cases where it's just we evaluate on a feature by feature basis, and then sometimes if you need it to be delivered quickly, it's faster to put it in the new stack and then eventually make sure it gets migrated. So yeah, it depends. Yeah.
One more question: are you building a new stack from scratch, or are you
Yeah.
using the?
No, so it's a very good question. So are we building the new stack from scratch? So yes, in terms of UI components, it's all React based. In terms of all the backend, I already covered all the architecture we use. So the new stack is completely built from scratch with all the latest technologies, with Webflux and reactive programming and all of that. Because this is a 16-year-old legacy code base which has just gone through so many journeys, and you saw how it's evolved over time. So you can see some traces of older architecture. The newer ones is now you have a chance to redo it again. Might as well as use what is the most current stuff in the market. So yeah.
This was a very nice session.
Thank you.
It makes perfect sense for a cloud-based
Mm-hmm.
platform. Does this mean that the on-premises product is entirely different code base?
Yeah. Okay, so the question was about the cloud base versus the on-prem code base. They were initially it was the same code base till they were on the VMs. As we started moving towards the AWS based architecture, we forked the code base. And because the challenges are very different for a product which is on-prem versus the product in the cloud. But not to say we still interact a lot with the on-prem, because if there is stuff which they can learn from us. So there are times when we are always sharing, certain important changes which we've made in one code base to the other. But yes, there are different teams working on it, and the needs are different. So yes, there is a point now that the code bases have been forked. And some of these new services which we are building is just very specific to the cloud product. These might not be the issues which an on-prem product might face. So yeah. So any other questions? Yes. Yes.
Performance and
Mm-hmm.
so how we are maintaining P95 5 millisecond actually?
In the new service? Okay. So having a monolith has its own advantages. I could tell you advantages in terms of, okay, single source code, tracing, we are like, when you have so many services, now you have to start figuring out correlating network calls and all of that. So those are the advantages with the monolith. How we are managing the performance in the new architecture is because of, this extreme caching, this reactive framework which has its own back pressure and the way it works. So it manages the thread pools. We use a lot of cache thread pools and we tweak all of those. That gives us the extreme performance which we want. So the monolith has its advantages, especially in terms of when outages happen. Tracing, because it's all single code base, you'll find it versus you would be looking. But the new architecture gives us a lot more benefits where we can scale out the schedule scaling. We did it in the new services and then we backported in the monolith. So there are the new services will definitely, because of the architecture which we are using, it gives us these extreme performances. So any other questions? Yeah.
How do you balance product requirements with SLA?
Okay. Yes. How do we balance product requirements with SLA enforcements? So yes, it's always a tricky. That's because product teams would always want to deliver features, and that's what our customers are looking for, right? This is all things which we are doing in the back to improve their performance, but our product teams would want to deliver more good features. So the way we balance it is some of this re-architecture work is done by independent teams. Most of the teams would still be working on the monolith, and depending on new features, like I answered in the previous question, if it could be added on the new stack, it gets added on the new stack. Otherwise they might still have to make a choice and add it on the old stack. So right now, if you see, not everybody is working on the new re-architecture, and also we are still taking care of our customer needs and what the product teams are asking. But parallelly, we know that this is the vision we have to get to, and we've already started paving the path for that. So yeah. SLAs? New services? Okay. Yeah, how do we enforce the SLAs? So right now the new services are being built by a small team, and we are the ones who are building it. So we've learned over time also, and we are extremely conscious about these latencies. So anytime we are architecting or a new service, the first thing we do is document what are our expectations, or especially in terms of latency. We define these as tiers of service. If these are all tier 0 or tier 1 services, means if they cannot go down. If they go down, it is going to impact the customer. There could be tier 2 or tier 3 services, which, if they go down, the customer is not going to get majorly impacted. So whenever we start a new service, we will have these SLA requirements. We'll define the tier for the service. So that helps us plan, how critical these services are and what the SLA requirements are. Does that answer? Yeah.
Do you do performance testing?
Yes. Yes, we do. We do. So this is a complete DevOps. So all of us, there is no QA. In a way, this is fantastic because we are just a few of us who are on call. So we are, and we get paged. So right now it's a very senior team, and we will be doing performance and load testing. So because when we are defining these SLAs, we have to make sure that the system can handle it. So we use Gatling, and then we'll have, okay, if that was what you're looking, I can see a lot of nods. So yes, we do use Gatling, JMeter. We would use Apache Bench also locally to check, this throughput, what are the latencies we get. So all of that we do.
I think my question was about performance testing being integrated in the continuous delivery pipeline.
Yes. Yeah. So we do that also. So the way it was, we have these different environments where code is deployed. The first would be the dev environment. There would be staging. And on staging, we would have these tests. You don't have to run all the time these performance tests. So, but you could have it on a specific period of time, but all that is automated. So if you need to deploy a new code, and if you want to see how the numbers would look, we could do it. And then we also do these progressive rollouts. We do region-based deployments. So, I could just try it in one region, say US East or Prod EU or one of those regions, see on peak traffic how we behaved, and next day roll it out to other regions. So all of this combined is what we use for performance. Yeah. Any other questions? Okay, we have 4 minutes. If you want to ask anything, feel free to reach out to me. And of course, Atlassian is hiring. If there is anything, if this is something which is interesting to you, definitely reach me out on Twitter or LinkedIn. So thank you for attending this talk.